Hello, pre-calculus students. A little bit raspy today with the uh, winter blast that we've been experiencing. I hope that everybody's doing okay. Uh, I'm finally with power, so I thought I would go ahead and give you the lectures that we missed for this week, week number 5. That way you'll go ahead and have the content um, and be ready to move forward as we start next week. I wanted to go ahead and get this information out and just basically remind you that, again, this is a review from college algebra, and I want to make sure that we have all of our ducks in a row. Now, when you take calculus and you work with polynomials and algebraic functions, this kind of work is very useful, but it tends to be work that most of you remember. So what I've done is I prepared a lecture, and I want to go through it where I don't write as much so you can actually get to the thick of it to be able to do your problems and be able to make certain conclusions about what you're doing. So let me go ahead and share my screen. What we're going to do is start with just basically real zeros. We've been doing this from the beginning of class, but now we just want to make it a little bit more formalized. And what I did is I've taken the basic ideas from the sections in 3.4 and 3.5. And what I want to do is basically, well, actually, let me check here. That section on the complex zeros, imaginary, yeah, it's actually 3.6. Excuse me, I said 3.5, but this is 3.4 and 3.6. And so what we want to do is basically summarize what you did in college algebra and then maybe capitalize on a few things that may be a little new and help you to make for a better understanding. So simply, when it comes to real zeros, what we're going to do is just like when we did the division algorithm, we're going to look at the polynomial in the standard descending form. And what we're going to say is that when we have a real polynomial, all of the coefficients will be real numbers. Now, if we want to figure out how to basically solve for zeros of a polynomial, there is a special result called the rational zeros theorem. So what I've done right here at the very beginning is I've assumed that we have an integer polynomial. So real polynomials include everything: the integer polynomials, the rational polynomials, and of course, polynomials where you might have a coefficient of the square root of 2. So that is a big umbrella. However, the real polynomials don't include the polynomials that have imaginary coefficients. That's where we make the umbrella a little bit bigger and we talk about the complex polynomials. So a very important theorem that you talked about in college algebra was the rational zeros theorem. And so basically what it said is if we start with an integer polynomial and we assume that P and Q are integers. And another important thing is that we're going to make the assumption that P over Q as a fraction is reduced. So what I've written here is I've called them relatively prime, like 2/3. We wouldn't have something like 2/4 because that's not reduced. The reduced form would be 1/2. So we're looking at the reduced form P over Q. Now, what we want to do is come up with a way to figure out if a polynomial that has integer coefficients actually has rational zeros. That is, zeros that are fractions of integers. So what we do is we assume that polynomial P has a zero P over Q. And you can think of the P here as a lowercase p and the name of the polynomial as an uppercase P. So if it is indeed true that P over Q is a zero, then P must divide the constant term and Q, the denominator of the fraction, must divide the leading coefficient. Now, one thing that's very important here is that we assume that A sub 0 is non-zero. A sub 0 is non-zero. Because if it were actually 0, we would just, the first term would have an x, and so we'd back to the x, and this would become the constant term, A sub 1. So we always make the assumption that the A sub 0 is a constant term. Otherwise, as I said, we would factor and then proceed to look at the polynomial that had A1 as a constant term. So that's what we do. Now, I'll say more about how we do this when we have these divisibility results here. Then it tells us how we can make a list of possible candidates. And what I've written here is we use this theorem in reverse. That is, when we think about solving for rational zeros, we compile a list and then we can check the list with synthetic division. Now, before we actually employ this, I want to get another result on the table so that we can use it if necessary. Now, these results don't tend to be as pivotal in the solution process, but they give us ideas that can help, especially when it might be a little bit difficult to find zeros, rational zeros. So it's called the Descartes rule of signs. Now, in terms of a proof, affecting a proof of the rational zeros theorem is fairly reasonable. The Descartes rule of signs actually uses Rawls' theorem from calculus. And so this theorem is a little bit more complicated to prove, but is a very, very useful result. So what we're going to do, what about rational zeros? Okay, helps us to find rational zeros of a polynomial if they exist, integer polynomial. Descartes rule of signs will help us to determine the disposition of real polynomial zeros. So again, we're working with a real polynomial, and most of them will be integer polynomials. That's just how it is when you're studying this in pre-calculus. And what we want to do is check on a function called variation in sign. So what I've done is I've called it var for variation. So we're going to move from the real polynomials into the non-negative integers. So basically the counting numbers 1, 2, 3, 4, including 0. And so what is var going to do? Well, when you look at the real polynomial, you're basically looking at the number of sign changes in the coefficients of p. So you start like with the leading coefficient, and you just move through the polynomial. And if the sign of the coefficient changes, that's a tick mark. So as it changes, you keep track of all those changes. That's called the variation in sign. That's fairly simple to do, but the monumental result of Descartes rule of signs is the following. The number of positive zeros, again, we're talking about real zeros, you get 0 or you get positive or you get negative. And so the positive zeros will either be the variation in sign of p or the variation in sign minus an even whole number. And here's what's important. This expression here is always non-negative. Once it starts to go into the negative realm, then you don't worry about it because it doesn't make sense. You can't have -2 positive zeros. Now, what's nice about this is it's easy to execute. For the negative zeros, we simply replace x with its additive inverse. Here I didn't even put of x because it's just plain old p. But what we basically do is a reflection in the y-axis. And so we can keep track of the negative zeros by looking at the variation in sign of p of negative x. And of course, the other possibilities would be that number less by an even whole number. And then of course, we always want this to be non-negative. So you're thinking, wow, well, that seems so simple. It can't be true. Well, it is a major result and a very beautiful result. But like I say, it's easy to execute. It's easy to actually apply. And you're going to find that it's fairly interesting as we work through some of these examples. Now, what I did, ladies and gentlemen, is I took a real simple example here. Let's take a polynomial that's quadratic. And I have 2x squared plus 7x plus 4. And now when we look at this, we think, okay, how do we do this? Okay, first, let's see what Descartes' rule of signs says. We really don't need this. I mean, we thoroughly understand the quadratic polynomial. There's nothing about it that we can't figure out, but this makes a good example for variation in sign. Now you notice here, as we start here at the 2 is positive, and as we move through, the coefficients never change sign. That is, each of the coefficients as we move from left to right are all positive. So we say variation in sign is 0. That means there are no positive zeros. So that can be very useful. Maybe if you're just trying to figure out, you're doing a physics problem or an engineering problem, and you're thinking, well, you know, I don't even have to think about positive zeros because Descartes tells me there are none. Now let's look at P of negative X. Well, we just replace X with its additive inverse. So of course, all the even powers absorb the negative. So that's easy to move here, but the odd powers will retain it. So we get a negative 7X. And of course, the 4 doesn't change. Now what we can do is we start here, 2 to negative 7. That's one change. And then negative 7 to positive 4. That's the second change. So when we look at variation of sign, we have 2 for P of negative X, but then we can say, or less than by an even whole number. So we can now subtract 2, and 2 minus 2 is 0. So Descartes says they're either 2 negative zeros or none. Now, we can go ahead and figure this out. We don't have to guess. So if you look at the original polynomial here, let's just look at the discriminant. B squared minus 4AC. So when you square the 7, you get a 7 squared, that is a 49, minus 4 times 2 times 4. So no common factors. I can't factor it to death. 49. And then, of course, we have a 16 times a 2, which is a 32. So this will give us a 17, which is a positive number. So now when you look at this, you're thinking, oh, now we're going to have to use the quadratic formula. But we don't even have to think whether or not they're going to be negative. The idea here is that when we look at Descartes, we know that we're going to get 2 negative zeros. And so this, again, we might say, oh, maybe we get 0 because the discriminant is what? Negative, and then that would mean an imaginary 0. So now we can see that indeed the case is 2 negative zeros. So Descartes gives us a way to actually check on these things. That is, maybe we've got a higher degree polynomial and we just want to see about the disposition of zeros. So of course here, if it turned out that we had no negative zeros, then the alternative to that would be 2 imaginary. And I just want to remind you, for the real polynomials, because of the quadratic formula, all imaginary zeros will occur as complex pairs. And so if you're dealing with a real polynomial, you can never have one imaginary root. They will have to occur in 2s. Okay, so that makes it easy to fill in a chart if you're thinking about the Descartes rule of signs. Now, I wanted to just go ahead and look at some examples, again, which would be a simple factoring example that you don't need all this additional information to do, but just to remind you where we've been. But before we do that, I want to also talk about bounds for the real zeros. Again, if we have a polynomial that's real, that is, the coefficients are real, can we find real numbers A and B that provide a lower bound and an upper bound for the zeros? That is, P of C would be 0. Now, you might be thinking, is this a really precise theorem? Well, it's not a calculus theorem in the sense of precision, like a least upper bound or a greatest. For instance, we might say least upper bound or greatest lower bound. We're not going to have that kind of precision. It's not a calculus result. You could actually prove this using the division algorithm. Remember, division algorithm, big hammer. So the idea is that when we actually execute the synthetic division, there is a way to figure out when we possibly have either the upper bound or the lower bound. And how do we do that? Well, that's why I say when you do your synthetic division, that you do your addition either in your head or as a sidebar, so that you only produce rows that give you good information. That's why I always insist on that. And so what this says is, and let's just take this for what it's worth. We will always assume that the leading coefficient is positive, okay? So if it's not, factor it. Factor the negative, it's not gonna make any difference. The zeros will still be the same. So without loss of generality, that's my little shorthand, log, without loss of generality. And so now what we want to do is look at these cases. If B is a positive number, okay, B is a positive number, and we do the synthetic division in this case, that is divide by X minus B. If the entries in the synthetic row that we generate are non-negative, it'd be 0 or positive numbers, then this says that B is an upper bound for the real zeros, okay? So you might be able to say you already know the real zeros and you execute this and you don't get that non-negative row. But like I was saying before, is that this theorem is not very, very, very precise in the sense that it just, bam, it's going to give you a least upper bound. It will just give you a bound. And sometimes that's better than nothing. So like I say, it's not the end all theorem, but it's certainly a way to cut down on work when you're looking for rational zeros. Now, if we take a less than 0 and we divide the polynomial by X minus A, that is, we do the synthetic division, then the entries in the synthetic row, if they alternate non-negative, non-positive, that's again why we start here with this assumption, non-negative, non-positive, back and forth, alternate. If that's the case, if we get that pattern, then A is a lower bound for the real zeros. And the thing is that when you get zeros, if you have a 0, you can refer to the 0 as either positive or negative. So you have that flexibility. So again, this may not be earth shattering. And you look at this and say, okay, yeah, well, what if all the zeros are positive? I mean, if we test this out, will we get -1 as a lower bound? Possibly. Okay. The idea here is that this doesn't tell you what kind of number. I mean, it could be a positive number, but what we're going to normally check are nice numbers, not the square root of 2. So again, this result is not overly precise, but it certainly can be helpful when you're looking for rational zeros. Now, what I wanted to do with this next example is show you where we've already been. Say you have a 4th degree polynomial. This is a real polynomial. And when we look at this, we have 4x to the 4th minus 37x squared plus 9. Again, this is quadratic in x squared. And so I've written over here in red, solve by factoring. Now, when you apply these results that we've just discussed, apply them when you need them. Okay, because when you look at this and say, well, that's a quadratic equation, basically. It's quadratic in x squared. So, I think I can factor it. Let's try Professor Ron's AC lemma. Well, AC will give us a 4 times a 9. Well, we kind of go to the extremes now because we need a -37. So we're thinking, okay, let's just write 36 as -36 times -1. Now that's kind of a cheap way to write 36, but it gives us a sum that's -37. So we can go back to the original equation and rewrite the middle term. But since it's so simple, I mean, when you think about this, you're like, wow, this is really nice. For -37x squared, we have -36x squared minus x squared. And then of course here we factor the 4x squared, and here we just factor the -1. And now when you look at this, we have a common factor of x squared minus 9 times a 4x squared minus a 1. Now you might be thinking, what's Professor Ron doing here? Well, I'm doing like a complete factorization, which is something we're going to talk about as we proceed into the next section. So I might as well go ahead and introduce it now. You're thinking, I can factor this as a difference of squares as 2x minus 1 times 2x plus 1. So what I did is I just factored the 4 here. So we have x squared minus a quarter or 1/4. And again, that's a difference of two squares, which we can factor as x minus 1/2 and x plus 1/2. And of course, this x squared minus 9 is also a difference of squares, x minus 3 times x plus 3. So what I've written here is complete factorization. Now, I haven't put in all the negatives here, but basically x plus 1/2 could be written as x minus negative 1/2 and x plus 3. So I'll just go ahead and write that in. This could be written this way. Kind of overkill, and of course we could write this way. So basically what I'm saying here is that theoretically, we should always be able to do x minus the zeros, where the zeros are 1/2, negative 1/2, 3, and negative 3, which I've listed here, all of multiplicity 1. All of multiplicity 1. So we know at each zero, we would cross the x-axis. You know, that's such a useful thing to use when you're doing the BB technique. You don't have to work as hard. You get the extremes and boom, you just run it through. You just have to check the extremes. If you got zeros, that'll either bring you to touch the axis or cross it. So that's always a nice feature when you're thinking about looking for zeros and then, of course, testing for sign. Now, so in this case, we didn't take out any of the big guns. We factored it very nicely, very completely, just using what? Factorization techniques, Professor Ron Seelemmer. Now on this next one, what I wanted to do, ladies and gentlemen, is kind of just see what we could do if we had a situation where factoring really didn't present itself. And what I did is I just picked a problem from your book. And the problem is an integer polynomial, but look, 3x to the 5th minus 14x to the 4th minus 14x cubed plus 36x squared plus 43x plus 10. Now, when you look at that, notice under here in red, I actually worked this problem two different ways, but I said observe -1 is a 0. The thing is that if you check the coefficients, it's usually pretty simple to figure out when 1 is a 0, because of course all the coefficients would add to 0. And if -1 were a 0, as long as you flip the sign of the odd powers. But when you think of this, we can just do a little tabulation here. Watch this. I've said -1 is a 0. Here's a quick way to check it. Remember, all the odd powers will give you negative. So we have -3 minus 14 plus 14 plus 36 minus 43 plus 10. Now, when you look at all of this, we see what we need to get. Now, notice these two absorb. And here, when you look at these, that'll give you a 33. And then, of course, this gives you a -33. So that gives you 0. So checking 1 and -1, really very simple. And sometimes it's worth your effort, because if you've got a cubic polynomial, you can automatically reduce it to quadratic, and then you're done. Because once it's quadratic, we know quadratics. So what I wanted to do here is make this observation, but I didn't use it firsthand. I used it in a second attempt to do this, just to show you variety of ways to work these problems. But what I wanted to do was kind of take some of the ideas that I mentioned at the beginning of the lecture to show you how we can use Descartes, maybe in the bounds theorem. Again, don't look at these as things that you have to do. Just look at them as ways to maybe eliminate certain dispositions of zeros. So first, we look at the variation of P. So we start with the plus, so we have 1, 2. Only 2 variations in sign. So this is going, and notice here, I checked one, but I put lines through. I'll show you what that means. So we either have two positive zeros or we have what? 2 minus 2 or no positive zeros. So here in the pluses, I've just got 2's and zeros. Okay. I can't really fill in anything else yet until I know the negatives. But I know in this column, I can only have 2 or 0 because of Descartes. Now, let's look at the variation of P of negative X. Okay, now remember, when we do that, we just make sure that the odd powers get the negative, the even absorbs. So we have the negative here. So I'm going to go ahead and write it down. No change, negative, negative, positive, no change, negative, no change. And now when you start negative, there's a change, 1, 2, 3. So we get variation of P of negative X is 3. So if we subtract 1, excuse me, if we subtract 2, which is an even whole number, we'll get 1. And of course, you keep subtracting, you get negative. So we stop just like we did here. So now when we look at the negative zeros here, we only have 3 or 1. So when you think about that, what are the possible dispositions of real zeros, including the imaginary, can we have? Again, remembering that the imaginary will have to occur in pairs, conjugate pairs. So for instance, degree 5, fundamental theorem of algebra, we're going to have 5 zeros, including multiplicities, which is basically the next section. So we do the next section while we're doing this section. So it's really nice how it works together. So we could have the max in each. For instance, we could have 3 negative, 2 positive. That doesn't leave any room for imaginary. And you notice I put a circle around this. Well, let's not let the cat out of the bag, but I'm showing you how we generate this. Okay, well, up here we could have no positives. We could have 3 negatives, and then that would leave room for 2 imaginary, which makes sense. Okay, well, let's try another one. We can have another 0 for the positive, or we could use 1, and that's going to leave 4 for the imaginary. Again, 4 is an even number, complex conjugate pairs, that works. Or the very last one, we just think, what are the other possibilities? Just as long as we get an even number here and we're choosing 0 to be even. Here we're going to think, okay, well, what's left? 2 positive, 1 negative. That'll work. Again, that leaves 2 for the imaginary. So the thing is, as you work through the rational zeros theorem, you may be able to eliminate some of these. So when you look at this, you're thinking, okay, well, is this really a big help? Well, it's better than nothing. And it kind of gives you an idea of how you can proceed. Now, when we look at the original theorem or the original polynomial, what we want to do, again, is generate a list. Remember, I always do it like this, P over Q. The numerator of a 0 must divide the constant term. The denominator of the 0 must divide the leading coefficient. So when we think of positive or plus or minus, positive and negative integer divisors, we can go through the list for 10, plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. Now, 3 is a lot more user-friendly, plus or minus 1 and plus or minus 3. So we just think of ratios of these P's and Q's. Okay, if we divide everything by plus or minus 1, we just get the P list here. And then, of course, if we divide by 3, well, none of these numbers is divisible by 3. So we get the 1/3, we get the 2/3, we get the 5/3 and the 10/3, all with the plus or minus. Now, at this point, one thing we can notice, again, if you look up here at the zeros and you replace the X with 1, you can see when you add these that you don't get 0. So take the time to check. It's like, okay, well, I know 1 doesn't work. So if I'm going to look for positive zeros, I'm going to start with 2. Don't start with 1. You're just wasting your time. Now, again, we may or may not use the bounds theorem, but if we get something that's nice, we work with it. Okay, let's try 2. Let's do the synthetic division. Bring the 3 down. 3 times 2 is 6. 6 plus negative 14, negative 8. That's the process. Do it again. Negative 8 times 2 is negative 16, plus a negative 14 is a negative 30. Okay, keep going. Negative 30 times a 2 is a negative 60, plus a 36 gives us a negative 24. Keep going. Negative 24 times 2 is a negative 48, plus a 43 gives us a negative 5. And lastly, negative 5 times 2 is a negative 10, plus 10 is 0. So I put a check there saying that now by division, we have a remainder of 2. Therefore, 2 is a 0. And by the factor theorem, x minus 2 must be a factor. And then, of course, we get the reduced right here. So we have the reduced polynomial, 3x to the fourth, negative 8x cubed, negative 30x squared, minus 24x, minus a 5. Now, when you think about this, it's like we've improved it a little bit. We got a slight improvement. We still have the 3 here, but we got a minus 5 and only 2 integer factors there, plus or minus 1, plus or minus 5, actually 4, but still they're just 2 numbers in absolute value. So that's less work. And then, of course, the 3, we get the same thing. So once you find a 0, you now work with the reduced polynomial. You now focus on the polynomial of a lower degree. You don't just keep working on the same polynomial. That doesn't put you in the right direction. You want to be able to now try to reduce this particular polynomial. Now notice, when we look at our list over here, we get the 1 and the 5 plus or minus, but then of course we divide by the 3 and get the plus or minus 1/3 and the plus or minus 5/3. Keeping in mind already, we know negative 1 works. Okay, so that's a freebie. We've already shown that. So what we're going to do, and I'll show you why we just kind of fall on that. But at this point, we're thinking, okay, well, 1 doesn't work. If we're going to try a 5, a positive number, let's avoid the fractions and just see if the bounds theorem helps us out. So let's try the 5. It looks like, no harm in trying 5. Okay, so we have 5, and we put our coefficients in descending order right here on the tableau. You can call it the table or the tableau. So bring the 3 down. 3 times 5 is 15, plus a negative 8 is a 7. Do it again. 7 times 5, 35, plus a negative 30 is 5. And then 5 times 5 is 25, plus a negative 24 is 1. Well, that's pretty good because 1 times 5 is 5, plus a negative 5 is 0. Now notice here, see all this non-negative. The bounds theorem says, don't do any more. Don't do any more. I mean, you're not going to find any positive zeros bigger than 5. And we got lucky here. We got lucky right there. Okay, sometimes it's very robust and very useful. Other times it may not be as precise, but that's just the way that a theorem works. Now we have, not only do we have 2 as a 0 and 5, we've got our reduced polynomial right here. 3x cubed, 7x squared, 5x plus 1. And now you're thinking, Professor Ron does this, but we've got back in our hip pocket that we know negative 1 works. But here's why, even if you don't recognize that, the next step is very useful. Look here, this is amazing. The p plus or minus 1, and then of course the q plus or minus 1 plus or minus 1/3. Let me silence my email because that's just gonna haunt me. Let's see here. Let me get rid of that. And then I'll come back. Let's see here. There we go. I love the email, but I don't want it dinging while we're trying to do our mathematics. Okay, so now look at this. Look at this. When we look here, we're thinking, okay, well, we've got not a whole lot of work here. And we're thinking, okay, well, 1, we know that doesn't work. We already checked that. 1/3, it's a lot of work. Negative 1 looks pretty good. So again, even if you didn't do this, you're thinking, let's start easy. No reason to think that there aren't any negatives. I mean, by Descartes, we know we're going to have at least 1 negative, okay? So there's no harm in trying a negative. So we try -1. Okay, remember 3, 7, 5, 1. Bring the 3 down. 3 times -1 is -3 plus 7 is a 4. 4 times -1 is a -4 plus 5 is a 1. And then 1 times -1 plus 1 is a 0. Shazam. So now we have x minus 2, we have x minus 5, and now x minus the -1 or x plus 1. And our reduced is our friend, because it's quadratic. 3x squared plus 4x plus 1. And you're thinking, well, that's the nicest quadratic in the world, because now if you look at this AC, 3 times 1, 3 plus 1 is 4. So boom, that's how easy is that? So now we simply rewrite the middle term here is 3x plus x, and we can factor by grouping. We have 3x times x plus 1, and here we just have 1 times x plus 1. Common factor x plus 1, and then we have 3x plus a 1 right here. Now, like I said before, if you want, you can go ahead and have these all as x minus the particular 0, because what we're going to see with the complete factorization is that the number that's factored will always be the leading coefficient. So here, this 3 we can factor and expose the 0. So we'll have 3 times x plus 1/3. Now, of course, you don't have to put in the minus when you have the plus. It just makes it nice so you can see, you have a visual of the zeros, but that's not a big deal. The thing is that now we have a complete factorization. Sometimes they call this the linearization of the polynomial. So for instance, we might have zeros of multiplicity 2, but when you spread it all out, they all have multiplicity 1, where you could have some repetitions. So this is what we call the complete linearization. Now, I just want to say that when you look at this, what we have is a very nice situation of how we can use Descartes, the bounds, and the rational zeros theorem to affect this factorization. Now, just remember, there are some nice polynomials out there that have rational zeros, and they make your life a lot easier. But of course, when you take calculus, you could use this theorem, rational zeros theorem, to show that a particular polynomial doesn't have any rational zeros. And then you're thinking, oh man, if it's cubic, we're going to have to attack it with some calculus. And in many cases, the cubic polynomials we can rig to be 1-to-1. So that's a nice introduction to calculus theory next semester when you take that class. Okay. Now, what I wanted to do is look at a nice word problem. And of course, as I looked at it, I thought, because WebAssign will always give you a little way to work things. And I went ahead and kept it factored here. I raced and said, I'm going to keep this factored because we love things that are factored. It doesn't change the answer. It just makes it easier to find. So what I wanted to do is, when I looked through what Dr. Stewart had, I thought, what would be nice is to have a polynomial problem that's really characterizing a calculus problem. And so this will be a standard example that you do in calculus. But it's easy to set up, and it works well with the zeros. In calculus, you're just going to figure out which zero in this problem gives you the maximum volume, in the sense that what we want to do, you're thinking, well, they're giving us the volume here. So the idea is, when you do the calculus, you're not given the volume. What you're doing is taking the problem with a little more less given, and then moving it forward. And then you say, oh, Professor Ron, for this value of X, we have the maximum volume. Boom. That's where you're optimizing using calculus. So what we're going to do, ladies and gentlemen, is a problem that takes us into that realm, but still stays in the pre-calculus side. So let's look at it. This is a nice result. So we have an open box of 3,000 cubic centimeters is to be constructed in the standard way That is, we're going to take a sheet of cardboard or a sheet of something, maybe it's metal. This particular sheet will be 30 centimeters by 40 centimeters. And what we're going to do, as you see that I've noted here, we're going to cut squares in each of the corners. So cut squares of side X from each corner. And then we're going to basically fold up the sides to create a box. So when you cut out all of these squares, you just bend up the sides, and then you get out your duct tape or your glue or whatever, maybe a combination of the two to make a secure box. Now, of course, you know, if you're an engineer, you may have certain things that you do with your pieces of sheet metal or whatever that are configured differently so that you actually get a more secure box. So this can be changed in many ways from the vantage point of an engineer. So we're just going to look at it as a mathematical construct. So the idea is when you flip everything up, you're thinking, okay, what does that leave? Now, the WebAssign did kind of insist on this being the length side and this being the width side, just so that when you actually type your answers, you're in the correct box. That really doesn't matter, but it's good just to specify. And so now, if we take the 30 centimeter side and take away 2x, we get 30 minus 2x. And then, of course, you can factor the 2, which you know Professor Ron lives to do. That'll give you 2 times 15 minus x. Okay, before I talk about this, let's see what we get here. Now, in this case, we're going to get 40, or this 40 minus 2x, which will give us 2 times 20 minus x. Now, if we notice both of these factors here, of course, when we look at this one, we say, okay, if we want a non-negative answer, x must be between 0 and 15. And then you're thinking, okay, well, if x is 0, there is no box. It's just a piece of metal. And of course, if x is 15, then you got too carried away when you were cutting out the squares. Then there was nothing left. So you might think of these as strict inequalities, if you like. If the WebAssign writes them as strict, the upper bound here is still the same. I always like to look at things as non-negative, because I mean, you could do an example where you got no box or no volume or whatever, and that's certainly a possibility. And when you're designing things, you need to make sure that the dimensions are what they need to be, so you get something that's going to suit the purposes of what you're trying to do. So the idea now is to say, okay, if we say height of the box is x times the length times the width. So what we want to do is say, okay, so we do that right here with the 2's factored. And so what I'm doing is I'm just hitting the 2's here to give the 4, and then the x, and then the factor form here. Now, we have to multiply some of this out, but this is where I backed up and said, well, there's no reason to go ahead and multiply through by that 4, because we're going to have to introduce the 3,000. And why multiply and then divide? So that was kind of ridiculous. That's why I said I'm just going to do it this way. So when we look at this, all we have to do is multiply the two binomials here. So we have the 15 times the 20 here, 15 times the negative x. We have the negative x times the 20. And here we have the negative x times the negative x, which gives us this. Now, what I want to do is just simply combine the like terms. Here we get a negative 35. And then, of course, 2 times 15 is 30. And tack on another 0. That'll give us 300. And then, of course, the x squared here. Now, when you multiply, leaving the 4 outside, we get an x cubed minus a 35x squared plus a 300x. Okay, reasonable. That's what I put a red box around and called that the volume function, V for volume, independent variable x. Now the idea is we want our box to have this volume. So what we're going to try to do is set the V equal to the 3,000 and then figure out if there are actual values of x that exist so that we get a box. Okay, that's a reasonable problem. Probably not the best way to do it. You want to be able to figure out what kind of box you need, but this is certainly a good example. So if someone said they just need a box that has this kind of volume. You do your mathematics and you say, okay, well, this value of X will work to produce a volume here. So again, there are many ways to look at this problem and to look at it in ways that could be plus or negative, just depending on what you're trying to do. So now we simply set these equal, the function equal to 3,000. Now, that's why I left the 4 factor, because you can go ahead and divide by 4 and get 750. And now, of course, just move everything over, and we've got a nice polynomial equation right here, equal to 0. So now we actually get a new polynomial. So when we put in this equal 3,000, we're like, we need to analyze this. I don't give this polynomial a name. It's just that we know we need to find zeros of it. So when we look at this and we think, lots of factors here. So when you look at this and look at negative 750 times 1, you're thinking, okay, well, we got a negative 3 times a 25, we got a 5 times a 10. And I look at that and say, okay, we're not gonna beat ourselves up here and look at all these different factors, but we're gonna start out with an easy one like 5 and see what that gives us. Of course, if it doesn't work, we'll try something else. Clearly, 1 doesn't work, so that would be a bust to try that. And the thing is, we're thinking about 2, but I'm seeing all these multiples of 5s here. I'm thinking 5 probably going to work. So we do the 1, the negative 35, the 300, and the negative 750, and put our 5 here. Bring the 1 down. 1 times 5, 5, plus a negative 35 is a negative 30. And then negative 30 times 5, well, that's a negative 150, plus 300 gives us 150. And then, of course, jackpot, 5 times 15 is 75. So that gives us 750 plus a negative 750, which is a 0. So it's like cha-ching. A lot of times your intuition can help you immensely. Now, of course, we're like, all right, don't worry about bounds at this point. We didn't even worry about Descartes rule of signs. We're thinking, we're good to go. This now gives us a reduced polynomial here that's quadratic. And you're like, we know everything there is to know about quadratics. So what we're going to do is say, okay, well, we know that x equal 5 is a candidate. X equal 5 is going to give us a box with this volume. So that is one candidate. And 5, if we look up here, notice satisfies this inequality. So this, we can look at this and already say there's a winner right there. Now we're going to look at this quadratic and see if we get any more candidates. Again, A is 1, B is negative 30, and C is 150. And the nice thing about this, ladies and gentlemen, is that this uses the same techniques that I've been teaching you and that we've been using from day one. And so this is important in the sense that it just utilizes good mathematics. And so you can always check yourself. So when you look at the discriminant, b squared minus 4ac. So we'll have negative 30 squared minus 4 times a 1 times a 150. Well, these are easy numbers. We don't even have to factor them. 30 squared, the negative 30 squared will give us a 900. And then, of course, 4 times the 150 gives us a 600 with a negative. And of course, that difference is just 300. And now, of course, 30 times 10, but there's our perfect square, 3 times 10 squared. So now we go to the quadratic formula and we just substitute. So we have the opposite of b, which is 30, plus or minus 10 times the square root of 3. The square root of this, which we can easily now write as 10 root 3, divided by 2a. And so remember, the a was 1. So you can remember how we got the denominator. I'll move it up so you can see it. The a was 1. So now, of course, no reason to carry along all this baggage. Both of these numbers is divisible by 2. So we go ahead and divide. So 15 plus or minus 5 root 3. Now, when we look at this and we think about this, both of these numbers happens to be positive. because we have 4 times root 3. That's like, 5 times 1.7 approximately. So if we add that to 15 or even subtract it, we still have a positive number, but we know X can't be bigger than 15. So we have to discard this one. This doesn't make any sense with our routine for building the box. Now, of course, this number here is a number between 0 and 15, and I wrote here acceptable. Okay, so this is like doing the word problems from 1.7. Lots of times when you do the time, rate, distance, or you do the fraction of work, you'll get 2 answers and one won't make any sense because it's negative or something. It won't apply to the actual problem. So that's exactly what we have here. So now look, not only do we have 5 as a candidate, we have 15 minus 5 times the square root of 3. So we have 2. And so the last part of the WebAssign problem is just to say here, and let me do a refocus, get nice and sharp. And so now we can see that I'm using the same designation for length and width. We just substitute the value of 5. In this case, we have H is 5, and then 2 times 15 minus 5 gives us 2 times 10 or 20 for the length in centimeters. And then the width, of course, will be 2 times 20 minus 5, which gives us 2 times 15 or 30 centimeters. Now for the irrational value, again, we have this value for the height. The length will now just be, as we have here, 15 minus this number. So we've got plus here for minus minus. So the 15s go away and we get 2 times 5 root 3, which is 10 root 3 centimeters. And lastly, we replace, again, the X with this number. Minus minus gives us a plus. The 20 minus the 15 is a 5. Hit everything with the 2, we get 10 plus 10 root 3 centimeters. So basically we get 2 boxes. We get 2 possibilities. And so maybe we would go to the client and say, which of these dimensions would you prefer? Maybe the client needs, I don't know, 10,000 of these boxes. And you're giving them the option. So what you would do as an engineer or as an architect or as a STEM professional is you take a model of each box and say, okay, look at these boxes. They have the same volume. Which do you prefer for your company or whatever? And then they'll say, oh, interesting. I'm glad you did this. Well, I'll take this one. The idea is that maybe you could have just decided on your own which one, but options are good. And if your client thinks, well, my professional is keeping me abreast of everything that's going on, in the future, I'll be sure to ask him again for any projects that I do. And so, of course, that's always good. Okay, so we can see how working with polynomials, really, that's going to be a big part of what you do in calculus. And of course, you throw in the logarithms, the exponents, and the trig functions and whatever. But I thought this would be an interesting problem for you to see. And of course, you'll enjoy doing this with your WebAssign. Now, what I wanted to do, since we've basically already done all of this next section, the 3.4 will keep you busy. 3.6 just basically pulls in imaginary zeros and the fundamental theorem of algebra. Okay, so what we want to do, we're going to take P to be a complex polynomial. Now, let me just remind you, in this class, there is a WebAssign problem that gives you a polynomial that has an imaginary unit in one of the coefficients. In general, however, in most of the problems we do in this class, and of course in calculus, you're only dealing with real polynomials, okay? So, but this theorem is far-reaching. So even if you have a polynomial with imaginary coefficients, it's still true. Carl Friedrich Gauss was the first luminary in mathematics to produce this result. And then, of course, Galois, who was a 21-year-old brilliant mathematician who died in a duel, he developed Galois theory. So he probably had his own version of this. It's amazing that you in the book, they have a really nice write-up of this. it's amazing that you have a whole branch of mathematics named after you, and your age was 21 when you passed from this earth. Amazing. I mean, we can do what we do because giants in the field have preceded us and left us with so many wonderful tools to do mathematics. And we have to keep ourselves busy trying to see how we can use all these interesting results in the work that we do, and then come up with some nice modifications. So as a STEM professional, you'll be doing this. You're already doing it in this class. So now, what's the idea? If the degree of P is at least 1, then P has at least one complex zero. This problem says, this theorem says, every complex polynomial of degree 1 or greater has a complex zero. And then you're thinking, you do the synthetic division, chop it up, then apply it again. Do your synthetic division, chop it up again. So the idea is that we can get to the complete factorization or the linearization of a polynomial through subsequent applications of this result. So that's how we can just chop up a polynomial into nice linear factors. Even though some of the zeros might repeat in the sense that we might have a zero of a multiplicity 2 or 3, we can still always write those linear factors. Even if it's extremely difficult to figure out what the zeros are, we always know that they exist. This is a major result. And if you take a course in complex variables, you will learn a very nice result called Rouché's theorem, which will allow you to prove this theorem through the use of complex variable techniques. I can remember in that class, that was one of the most illuminating things we did, just because it took a theorem that's extremely hard to prove without it. You have to have a graduate course in algebra to prove the fundamental theorem of algebra. But if you do it with complex variables, it's something that you can actually prove before you get to grad school. So it's a very very nice result, and many people have studied it. Now, this is what I keep saying, complete factorization. You can take the leading coefficient, if you want to call it A, and just have these linear factors. So we might say that the degree of P is N, and so this means we would have N zeros, including multiplicities. So theoretically, we can always do that. So what I did was just list it there. And of course, I talked about it for 2 minutes before I even alluded to this, which is what I do, right? Okay, now what I wanted to do here is just do a complete factorization utilizing what we know. So we don't have any new tools yet. We're going to talk about those in the next slide here, but I want to just go ahead and say, okay, what if we had this polynomial? We have P of X is X to the 4th minus 11X cubed plus 38X squared minus 39X minus 1. Now, one thing that's very interesting here is we can do what we did before. Let's just go ahead and look at the variation in sign here. Okay, we start positive, so there's 1, 2, 3. Okay, so 3 variations in sign, so that gives us 3 positive zeros, or subtract 2, 1. So this column can only have 3 and 1. Now, if we look at the P of the additive inverse of X, remember the odd powers will flip sign. So we get X to the 4th plus 11X cubed plus 38X plus 39 minus 9, 39X minus 9. So let's check. So far, so good. Boom, right there, one change. So now we see the variation in P of negative X is 1. So there could be 1 negative 0. Okay, so doesn't leave you much flexibility, does it? So the Descartes is really, really good in some cases because it can minimize the disposition of zeros quickly. So now we know that there's 1 negative 0. So this column is just 1. And then that means we can flip-flop 3 and 1 here. So we either have 3 positive, 1 negative, that leaves no imaginary because we have a 4 here, or we could do 1 and 1 and then leave 2 for complex conjugate zeros that are imaginary. So Descartes says this or that. Of course, I put a circle around this. So let's just see why I did that and put a check by it. Okay, so now when we look at this, we think, okay, let's do our rational zeros. So we have a -9. So we've got plus or minus 1, plus or minus 3, plus or minus 9, and hallelujah, 1 plus or minus 1. So very good. So again, we just get this list right here because we're just dividing by plus or minus 1. Now, one thing you can notice here, and this is extremely important, if you look here, um, you want to check, okay, if we think of 1 here and adding all of these up here, we've got a -48, and that's going to give us, again, a -59. No way that we're going to get a 0 out of that with 1. So 1 doesn't work. I mean, we're like, nah, that's not going to work. So when we look at this saying, okay, well, we're either going to have 1 or 3, we're not going to start with 1 because we know it doesn't work. So let's try 3 because we're lazy, but let's see what happens. So let's try 3. Bring the 1 down. 1 times 3, 3 plus the -11 is -8. -8 times 3, -24, plus a 38 gives us a +14. 3 times 14, well, in that case, that's going to give us a 42. 42 plus a -39 gives us a +3, jackpot. 3 times 3 is 9, -9 plus 9, 0. So here we go. We look at this and say reduced x cubed minus 8x squared plus 14x plus 3. And then, of course, we know a 0 is 3. We have an x minus 3. Well, here we go again. Now the constant term is 3, so that means p can only be what? Plus or minus 1 or plus or minus 3, and we're still dividing by 1. So we've shortened the list from this one to this one. Well, 1 does not work. 1 does not work. We know that. Okay, so we go back up here and say, well, from Descartes here, we're thinking, well, do we have another positive 0? Well, let's check it out. The only one we could check would be 3. No harm in doing that. There's nothing else to check as far as rational zeros. Now, of course, we could end up having an irrational, and it would be, we wouldn't see it with the rational zeros theorem, but we're like, okay, let's check it out anyway. So let's try 3 again. Maybe it's multiplicity 2. So now when we look at this, we say, okay, here's reduced 1, -8, 14, 3. Bring the 1 down. 1 times 3 is 3. 3 plus -8 is a -5. -5 times 3, -15, plus 14, -1. -1 times 3, -3 plus 3, 0. Jackpot. So now what we're seeing, and this is really neat, we have a 0, 3, a multiplicity 2, and now we have a nice reduced polynomial. Again, we'll get x squared minus 5x minus 1. That's a quadratic, so there's nothing to do here. So when we look at this, we're thinking, okay, well, what does complete factorization say about this? Well, first it says look at the discriminant. And so we have b squared minus 4ac. So that's going to be, in this case, a -5 minus 4 times 1 times a -1. So the two negatives make the positive. That gives us a plus 29. So no imaginary yet. Imaginaries are good. We'll run into some. And so now by the quadratic formula, we get what? The opposite of b, 5 plus or minus the square root of 29 divided by 2a, 2. And that's, not a very attractive number, but it'll work. And now we can just go ahead and run it in. We'll just say x minus 3 times x minus 3. Those are the complete factorization. And then, of course, we have x minus the plus. So you just write it as a fraction. Don't worry about distributing the negative. You've got a nice fraction there. So you have x minus the 0. And then the second 0 has 5 minus root 29 over 2. So we have complete factorization, all linear factors. Fundamental theorem of algebra applied until we don't have anything left except a constant polynomial. And in this case, the 1 here is right out here, 1. It's just kind of a shadow 1, okay? So when polynomials factor, we're happy. But in general, we know polynomials, well, again, in general, polynomials are difficult. And I think you can have probably seen that in your past experience in college algebra, at least at the level that you were doing it. Now, what we want to do in this particular case, so remember what's nice about the imaginary zeros is that when you use the quadratic formula, you always know when you're going to get them. Okay, so if you've got a negative radical, right, you remove the negative and then you slap on the I on the exterior of the radical. And then if the real number can be factored, you can extract any square roots. You know, like if you have an 8, you know, you can extract the square root of 4, which is 2, and get 2 root 2 times I. So remember, I is the imaginary unit. Now, what I wanted to do here, again, we're going to do more with the complete factorization here, but I just wanted to remind you of some results that we've already been talking about, and they're not difficult to prove. The idea here is that lots of the results that we use in this class are well within our power to prove. However, the division algorithm is complete, is complex, I want to say. I don't want to say completely difficult, but it's more complex. Takes a little bit more maturity, but it's a good result. And of course, the fundamental theorem of algebra, a very difficult result to prove in generality. So that doesn't mean we cannot use the results. So now what we do, if we look at this, let's just go ahead and know that we've been using this. Imaginary zeros of real polynomials occur in conjugate pairs. This is a result of the quadratic formula. So when would you ever get an imaginary zero in a real polynomial? It means that you would have looked at the discriminant and the discriminant was negative, less than 0. So by virtue of the quadratic formula, quadratic factors are either going to give you real zeros, real, or what? Imaginary. I mean, you can get repeated zeros, you can get distinct real, or you can get the other extreme, which is 2 complex conjugate pairs, which gives you the imaginary case. So this actually, using properties of the imaginary unit, will actually always be true. So if you have a 0 here of a polynomial, a real polynomial, and you just call it a plus bi, then you automatically know that its complex conjugate, a minus bi, is also a 0. So if I tell you that you have a 0, in this case, 1 plus I of p, where p is a real polynomial, then this implies that 1 minus I is also a 0. So again, when you have complex conjugate pairs, you have some really nice theory that's on your side. So and what's another helpful result that we find in the theory of zeros of real polynomials? Here's one, and this saves you a lot of time. For instance, if you have to build a polynomial that has this imaginary 0 and p is real, that is, you want to build a real polynomial, then all of the imaginary zeros will be the consequence of solving a quadratic equation. And so the actual quadratic factor you can always build from the imaginary 0. That is, the quadratic factor responsible for this. We can even do it for this. Notice here, we have a equals 1 and we have b equals 1. That is, the coefficient of I is just 1. And when you write this down, we get x squared minus 2x, and then 1 squared plus 1 squared is 2. That, ladies and gentlemen, is the quadratic factor that gives rise to both of these zeros here. So instead of having to do the factor theorem and having to multiply out all those numbers, this theorem does it for you. The theorem proof actually is the multiplication. And so you can use this theorem to build polynomials more quickly using this result. And of course, there's a whole lot less chance of a mistake if you use this theorem than if you multiply things. So try that. I think you'll find it to be very useful. Now, let's go ahead and get to wrapping up what we want to do with this section. Let's do a complete factorization. Now, what I looked at with this particular problem is I thought it was kind of interesting. It was a cubic polynomial with some interesting coefficients. So if you look at this and you think about it, we've got P of X equals 2x cubed plus 9x squared plus 16x plus 15. And you're thinking, wow, that's an interesting polynomial because there's no variation in sign. Okay, so that boom right there, there are no positive zeros. Obviously, you could not replace X with a positive number and ever get zero because you're adding everything. So you know that, boom, you already know that. And then you're thinking, okay, well, what's the possibility here? We're thinking 1, -0, and 2 imaginary. 1, -0, and 2 imaginary. So you're thinking, that makes sense because you're thinking, well, could I have 3 negatives? And you're thinking, yeah, you could have 3 negatives, or you could have 1 negative and what? 2 imaginary. Let's go ahead and finish this off. Let's do P of -x. So I've got this here thinking, well, that's something we need to think about, but let's just see what Descartes says. Okay, so this will be a -2x cubed plus 9x squared minus 16x plus a 15. Let me stick the x in there. So this would certainly be a possibility, but notice here when we do the variation P of -x, well, we start negative, 1, 2, 3. So this implies 3 or 1 negative zeros. The idea is that I write this thinking, well, I bet that's what we get, but there's nothing that precludes us from getting 3 because 3 negative and no imaginary is certainly possible. We just know we have no positive. So I've written this here not to say that, well, that's what we're going to get. I said that is a possibility. So right here, we'll say this is a possibility. Because that's this case right there. So when we do our little chart, so we have plus, we have minus, and imaginary. Well, these are both 0, right? And then we could have 3, 1, 0, 2. So I notated this one right here. So we're either going to get this one or this one. Let's see which one. Well, I've kind of let the cat out of the bag. So now, when we do our P over Q, again, we have 15, not the greatest because we get, the 1, the 3, the 5, and the 15, but we have a 2 here, so we have a 1 and a 2. So we have this list when we divide by plus or minus 1, and then we get this part of the list when we divide by 2. And of course, these are all non-even numbers, so we don't get any, rest in this particular case. So what we need to do first is to say, okay, well, there is no, and I did several examples here. Notice we don't check any of the positives because we know they don't want to work or they're not going to work. So I started with a -3 because it seemed kind of easy. Now, here's something that's interesting about this. When we try the -3, bring the 2 down, 2 times the -3 is a -6, plus 9 is a 3. 3 times -3 is a -9, plus 16 gives us a 7. And then 7 times -3 is a -21, plus 15 gives us a -6. And so that didn't work. Okay, no big deal. So we didn't get alternating non-negative, non-positive. So let's try another one. Let's just go ahead and keep it kind of simple. Try -5. We'll bring the 2 down. 2 times the negative 5 is a negative 10, plus 9 is a negative 1, and then negative 1 times the negative 5 is a positive 5, plus 16 is a 21, and 21 times the negative 5, in this case, that's going to be a what? A negative 105 plus a 15 is a negative 90. Well, that's clearly not zero, but look, non-negative, non-positive, non-negative, non-positive, stop. So there would be no number less than negative 5 that would be a candidate. You know, the idea is that if there is a real zero that's negative, it's not going to be less than negative 5. So I said, okay, forget that. So let's try numbers that are greater than negative 5. So we'll go up to the list and I'll start with negative 3/2. Notice with the negative 3/2, we get a real interesting situation here. So we bring, but see, this doesn't really apply. This doesn't really apply to the case where we have non-negative because we're dividing by a negative number. So we don't really have a rule here, but I said stop because it doesn't appear that we're getting anywhere. So that's when I go to the negative 5/2. But look at this, we bring the 2 down, 2 times the negative 3/2, the 2's absorb. That gives us a negative 3 plus a 9, which is a 6. Multiply by 6, the 2 absorbs, so we get 3 times the negative 3, which is a negative 9, plus 16 is a 7. And then, well, this is going nowhere fast. So we get a negative 21 over 2. And then, of course, we have a 30 over 2, which gives us a 9 over 2. So that's no good. And when we try the negative 1/2, we don't get any improvement. So at least it appears that as I'm getting greater and greater, I'm not really going in a good direction. In the sense, this is not part of the theorem, but it doesn't seem to be the case that as I get greater, still negative, that I'm improving the situation. So I'm thinking, okay, let me take something that's less than negative 3/2, negative 5/2. So I'll try that. Well, lo and behold, look, bring the 2 down, the 2's absorbed, we get a negative 5 plus a 9, which is a 4. Now multiply by 4, the 2's absorbed, so we get a 2 times the negative 5, which is a negative 10, plus 16 is a 6. And now when we multiply, the 2's absorbed, so we have a 3 times the negative 5, which is a negative 15, plus 15, boom. So the idea is that sometimes when you use the rational zeros theorem, you have to be kind of clever about it because, again, when we divide by x minus c, or in this case, whatever letter we want to use, if it was x minus a and the a was negative, this is not part of the theorem, but we just see that this isn't going anywhere. I mean, we're thinking, okay, well, let's try something less than negative 1/2, but certainly not less than negative 5. So somewhere in between, which that was a good candidate. Now notice right there. So we get the x minus the negative 5/2 or x plus 5/2. So that's good to go right there. And then of course, notice we have the 2 from complete factorization. So we can go ahead and stick the 2 right here. And now what we want to do, so again, when we have the complete factorization, you can just go ahead and align the leading coefficient here and then just write all the x minus the zeros. Now what's left here? We need to apply, in this case, the quadratic formula. Now notice, and this is where this 2 came from. If you notice here, we've got a 2x squared plus a 4x plus a 6. Well, I could just stick it there and know that it's going to be there. But what's nice about this, there's 2 factors. So I got it for free. And now I've got my nice coefficients here. I've got a equals 1, b equals 2, and c equals 3. So when you look at the discriminant, you get 2 squared, in this case, minus 4ac. That's a negative number, less than 0. So now we get to use our imaginary zeros. So like I said before, we want to place the imaginary unit there to take up for the square root of the negative 1. That is, remember, I, by definition, is the square root of negative 1. And of course, by that definition, I squared equals negative 1. So there are all kinds of neat things you can say about the imaginary unit. Now, of course, when we set up the quadratic formula, we get the opposite of b, which is -2, plus or minus, again, 2 root 2 times the imaginary unit divided by 2a. And of course, all the 2's absorb, and we're left with -1 plus or minus root 2 times I. So now, like I said before, we can just go ahead and bring the 2 that we got for free right here and have x minus a -5/2, x minus the first imaginary 0, and x minus the second imaginary 0. Now, a lot of students say, well, can I use these nice parentheses and leave it alone? Absolutely. Or if you want, you can go ahead and distribute the negative. But what's nice about this format here is that you can, in these cases, you can read the 0 directly. But if you want to go ahead and distribute the negative, it doesn't matter. It's just, again, it's not like here, I didn't put in the 2 negatives. So I have to think, oh, the 0 is -5/2 because I need minus minus. But here, just to save yourself a little bit of time, you can just use extra parentheses. Again, the complete linearization or complete factorization of the polynomial is always possible. Sometimes it's just very difficult to write. And just remember that when you're asked to do it in this class, you will be able to do it. And so notice, and this is very important, if we were to stop with just a real polynomial, we'd have to stop here because we see as we move to the next level, we get truly polynomials with imaginary coefficients. That is, the constant terms here are actually imaginary numbers. So we move from the realm of the real polynomial into the imaginary. That is the complex polynomials makes a larger umbrella. That is, they also contain the polynomials that have coefficients that are imaginary, whereas the real do not. So the umbrella gets bigger and bigger and bigger as you broaden the field of coefficients. Okay, so lastly, to finish up, and then of course, what we'll do after this in my next lecture, I'll talk about rational functions and how to graph those, which again was something you did in your college algebra course. But again, these ideas are so useful in calculus. I mean, they're not overly difficult. They really aren't, but they are so useful when you are navigating the arithmetic and the algebra of calculus. It's just great to have these ideas back here where it's like you can move through the problem quicker, or it's like, well, this calculus better support this idea because, you know, this is really what's going on. What does the calculus give me that makes the problem even better? So just remember, all of this baggage that you learn in this class, you just take along with you to calculus to make your burden lighter, so to speak. Now, for this first example, here I just have a nice little equation here I threw in for fun, but this one is just building a polynomial. And notice here I said not unique, but this is similar to what we did with the real polynomials in 3.3. So notice here, we want a polynomial R to have integer coefficients, Z. We want it to have degree 4. Here are some of the zeros that we want. We want the imaginary 0, 5 minus 5i, and we want 1 to be a 0 of multiplicity 2. Well, that takes up a lot of space. So that we can already do. If 1 is a 0 of multiplicity 2, then we just get x minus 1 quantity squared. So that's not so hard. Now, this is where we get to use the theorem I told you about, which is really nice. Remember, we have x squared minus 2ax plus a squared plus b squared. That's how we get the quadratic factor using our theorem or our lemma. And so, of course, a is 5, b is -5. So here, -2a, that'll give us a -10. And then a squared plus b squared is 25 plus 25, which gives us 50. And so now here's the quadratic factor that now we have in our table. So again, we can't put in the factor x minus this number because it will put in imaginary coefficients, and we are required to have integer coefficients. So this is the way you get a real pretty polynomial but you have to pay the price for it. You have to bump up the power in order to put in the so-called quadratic uh, factor, which gives you the nice integer coefficient. So now when we want the quadratic factor for this number, we take this guy here, which is x squared minus 10x plus 50. Notice I said this is not unique because we're not specifying a particular point on the polynomial. So this is not unique, but that's fine. So now we have x squared minus 10x plus 50 times x minus 1 squared. And you're thinking, would WebAssign let me get away with this? Well, here's the thing. If you're running out of time, you know, on a quiz or whatever, you probably could get away with this, but let's just go ahead and multiply it out. Some computer algebra systems say write in descending order, and then they would kick it out if you didn't do it. But if WebAssign doesn't always specify, you can keep it factored. You just have to make sure that whatever you type is an integer polynomial, and this definitely is an integer polynomial. So we have x squared minus 10x plus 50, and if we expand this, this is x squared minus 2x plus 1. So now let's hit everything with an x squared and do some columns. So x squared, give us x to the fourth, x squared, negative 2x cubed, x squared plus x squared. Hit everything with a negative 10x. Negative 10x gives us a negative 10x cubed, negative 10 here, negative, negative, positive 20x squared, and negative here, negative 10x. Now hit everything with a 50. 50x squared, negative 100x plus 50. And so this way, everything's written in columns with all the like terms together. So we get x to the fourth, negative 12x cubed. Now we add these, we get a 71x squared, a negative 110x plus a 50. So of course, this would be in descending form. And what we know is this fourth degree polynomial definitely has those zeros. So again, building a polynomial, not unique, but certainly serves the purpose. So the main thing that we get from the fundamental theorem of algebra is the understanding of how imaginary zeros occur in real polynomials, how we can always completely factorize a polynomial into the leading coefficient factor times all the x minus c1, x minus c2 on down, all those linear factors of the zeros. And then, of course, we can use our nice little result here to save some time to understand the quadratic factor of imaginary zeros, just like we did like the square root of 2. You know, you have x squared minus 2 gives you irrational zeros, but the quadratic is still an integer polynomial. So it's the same idea at work. Now, what I wanted to do in closing is just to throw in a polynomial here, and I didn't do anything to it. You can use monic here. I wrote use monic polynomial 2. For instance, I could have divided everything by I and had a monic polynomial, but you know, this is your choice. So here's a quadratic polynomial that is definitely imaginary. This is a complex polynomial. We can't say real because these have imaginary units in them. So we want to solve it. It's quadratic. So let's just look at the quadratic formula. So the discriminant. So in this case, if you like, just write it down. A equals I, B equals negative 2, and C equals I. How interesting, right? Okay, so B squared, negative 2 squared, minus 4 times A times C. So we get an I squared here, but of course I squared equals negative 1. So now we've got 4 minus a negative, so we get a positive 8. Okay, there's our discriminant. And so now we just utilize the quadratic formula. So we have the opposite of B, which is 2, plus or minus 2 times the square root of 2. And of course, divide by 2a, which is 2i. And all the 2's absorb. We've got a 2 in every term. So we get I plus or minus 2, 1 plus or minus 2. Well, I'll get it right. 1 plus or minus the square root of 2 divided by I. Okay, now you're thinking, is that okay? Well, you know, it's all right. I mean, it's not wrong, but let's just say we make it a little bit neater. We just multiply by the complex conjugate. So hit everything with a negative I and a negative I. Well, in this course, the negative I squared is just the negative 1. So this gives us a 1 here. And then if you multiply by the negative I, you'll just get, in this case, a negative I plus or minus root 2 times I. So what this does is just give you the zeros. And so if you wanted to list them, you could say negative I plus square root 2 I, negative I minus square root 2 I. So when we solve polynomials with complex or imaginary coefficients, we don't change the technique. We just don't spend a whole lot of time with these types of polynomials, on these types of polynomials in pre-cal and cal. So if you end up doing engineering as your STEM profession, and maybe you study some mechanical or maybe some electrical engineering, you will definitely study complex variables, and you'll have an opportunity to spend more time with the imaginary unit. Okay, so like I say, the next lecture is going to talk about the good old rational functions and how we graph them, and I think that'll be very interesting. But this concludes what I wanted to say about the polynomials. So this should give you a big leg up on studying the polynomials in section 4 and section 6 of chapter 3. So it's been good, and we'll see you later for the next lecture. Take care, everybody.